is to another goal of shared savings programs is to create market mechanisms that favor high-value providers and essentially use purchasers' market power to drive that improvement. And then finally, certainly shared savings programs strive to be fair to providers, to payers, and of course to serve patients' interests. If any of those conditions is not met, a shared savings program is unlikely to even get off the ground, let alone be sustainable. So that gets us to the question of random variation and how it affects the ability to achieve these goals under a shared savings model. And so let's start by defining a few terms about shared savings and how random variation fits into it. So the first term I want to define is observed savings, right? And that just means the actual difference between a healthcare provider's costs and the benchmark, right? You add up all of the claims costs that are incurred by the attributed population, you compare that to the benchmark, and you arrive at a difference. And if the costs are less than the benchmark, then those are the observed savings. The real savings are those savings that result from actual improvements in the provision and coordination of patient care. Right? So real savings in this nomenclature, real savings are what we hope to actually reward in a shared savings program. And it would be nice if real savings always equaled observed savings. Then it would be very simple and we wouldn't have to worry about random variation. But within any provider population, patient population, there is going to be some level of random variation that drives differences in the total cost of care. And so random savings in this context means those savings that result from events outside the control or influence of the healthcare provider. So, so the healthcare provider can do all the right things, and there might be another healthcare organization across the street, and they do all the right things, and yet they still have different results because one of them just got luckier than the other one. So the way that these three concepts relate to each other is that observed savings would equal the real savings, that is the real change in healthcare costs that are driven by the healthcare provider organization, plus the random savings, which might either increase or decrease the observed savings. And another way of expressing that relationship is that the real savings, which we would ideally like to reward providers on, is the observed savings adjusted for some level of random savings, which is harder to isolate. So, in a very important concept when we talk about random variation, random volatility, is this question of the population size that we're dealing with. And I think this is a concept that's familiar to many of you, but the amount of random volatility that we have to contend with goes down as a function of the size of a population. So this graph illustrates the results of just a simple computer program that I wrote, which essentially flips a coin, a simulated coin, as many times as we might want. And then it repeats the experiment, in this case 10,000 times. Right? So when you flip a coin, which is a random act, when you flip a coin only 10 times, the range of possible outcomes, the percentage of times that you get heads or tails, is very, very wide. Right? You actually sometimes flip 10 heads in a row or 10 tails in a row. And so that's what's reflected here in this bar. Right? When you do 10 flips and you repeat that 10,000 times, sometimes you'll get 0% heads. Sometimes you'll get 100% heads. If you flip a coin 100 times, you never get those extreme results, but you still get a pretty broad array of possible results. And again, this is all driven only by random chance, right? The coin is the same every time. It just happens to come up in this, more heads or more tails more frequently when you have fewer flips. And then as the number of flips increases, you see that the range of possible outcomes decreases pretty rapidly. And in fact, it's not a linear relationship. The decrease in random volatility is fairly rapid as you go from small sample sizes to large sample sizes. And so when we talk about shared savings, we can replace the number of times we flip a coin with the number of patients that are in the population. And within any population, some patients will have lower costs as a result of random luck. Some patients will have higher costs as a result of random luck. If we have a large enough population, we would expect much of that to cancel itself out, but as the population size decreases, we're more exposed to random variation. And that's a theme that we'll come back to again later. So let's, taking the definitions of a shared savings program and how those work, let's just walk through a case study of observed savings, real savings, and the impact of random variation. So imagine we have a shared savings program, and we've set a benchmark, right? So if you're, if you're at 0%, that is, if you're at trend in this example, you would have no savings. If you beat trend, your savings would be, 1% or 2%, depending on how much you beat trend by. Or if you were above trend, then you'd have a negative savings. So let's take a hypothetical provider organization, and their observed performance is that they beat trend by 2.5%. So good for them. Their observed savings is 2.5%, and so theoretically we would reward them in a shared savings program based on that gap between that 2.5% savings that they generated. But once we introduce the idea of random variation into the equation, we realize that what we observe as their performance might not be what the real savings are. They might have gotten lucky or unlucky, and so this observed performance might to some extent be the result of that good or bad luck. So in this illustration, if they got lucky, this is the range, this distribution is the range of what their possible real savings was. And in fact, they might have generated 0% savings, but because they got lucky, they appear to have a 2.5% savings. Conversely, they might have actually generated real savings more in the 5% range, but got unlucky, and so their observed savings turns out to be 2.5%. Now, I want to point out here, too, that there is a probability distribution associated with this, that the farther you get from the observed performance, the less likely that the result is. So while it's possible that they had, in this illustration, while it's possible that they had 0% observed savings, it's actually pretty unlikely. But it's certainly possible that they only had 2% savings or 1.5%. So one consequence of this is that as observed performance increases, we're more and more confident that at least some of the savings are real, right? So if this provider organization had generated about 4% of observed savings, we'd be highly confident that at least the first couple percent of those are real savings, because they really fall outside the range of possible random variation. But again, we'd be less confident as we get up to that number. And as performance improves, we can be more and more confident about that the savings are real. But let's return back to our original example, right, where we had observed performance due to random variation. Now, this might reflect the range of possible results associated with a medium-sized provider organization. A large organization, as we've already seen, we would have much less volatility associated with that larger organization. So here we could be much more confident that if the observed savings were 2.5%, that most of those savings are real, because it's unlikely that random variation would produce that much of a shift from the observed savings to the real savings. The flip side of that coin is that if we have a small organization, then we really are not confident at all about what the real savings would be. That we can observe 2.5% savings in that example, but it's hard to know how much of that was due to random variation and how much of it is real. It's possible in this illustration that the organization actually would have generated a negative savings except that they did get lucky and ended up at 2.5%. These curves, by the way, represent organizations of about 1,000 members for the blue curve, 5,000 members for the red curve, and 10,000 members for the green curve. So again, you get a sense of the fact that random volatility diminishes pretty rapidly as you're able to add to the sample size for these populations. So we've just gone through this example that illustrates the uncertainty that we have in essentially trusting the number, right? So we've calculated a provider organization has generated a certain savings. We want to reward them for having generated that savings, but we want to trust the number. And that lack of trust does create some problems. For payers who are writing these checks, it's important to them that they avoid paying rewards for randomly generated savings. As a policy matter, this is important because there's nothing sustainable or real about those savings. So we really do want to insulate payers from writing checks for a healthcare system which we already know is more expensive than we can sustain. We want to avoid paying additional money in for improvements that aren't real. It's also a problem for the most part for providers, right? Because they're just as likely to get unlucky as they are to get lucky. And so if they get unlucky and they've invested all this time and effort in improving care processes, improving patient outcomes, and then don't generate any savings because they've got unlucky, that's going to be a difficult result for them to accept, and might make them less willing to take on these kinds of risk arrangements going forward. Now, there is sort of an unusual situation for providers where if they've already made all the investments to implement an accountable care organization, for example, so if we can treat those investments as sunk costs, and if they're in a one-tailed shared savings arrangement where they only can get rewards, they wouldn't ever get penalized, then those providers actually would want to see as much random volatility and variation as possible because it maximizes their expected value of shared savings payments. Even though in that situation providers might prefer more random variation, I think we can all agree that that's really not the goal of the system. So we all have an interest in trying to control for these issues. So what I'd like to do now for the next part of the presentation is walk you through a number of the different methodologies that have been tested or incorporated into shared savings protocols around the country. Many of these are part of the Medicare shared savings programs. Others have been piloted in different state programs. And a couple of them we've developed here at Discern, and I'll spend a little more time explaining those as I think that they won't be as familiar to you as some of the other ones.